Vector quantization is a classical quantization technique from signal processing that allows the modeling of probability density functions by the distribution of prototype vectors. It was originally used for data compression. It works by dividing a large set of points into groups having approximately the same number of points closest to them. Each group is represented by its centroid point, as in k-means and some other clustering algorithms. The density matching property of vector quantization is powerful, especially for identifying the density of large and high-dimension data. Since data points are represented by the index of their closest centroid, commonly occurring data have low error, and rare data high error. This is why VQ is suitable for lossy data compression. It can also be used for lossy data correction and density estimation. Vector quantization is based on the competitive learning paradigm, so it is closely related to the self-organizing map model and to sparse coding models used in deep learning algorithms such as autoencoder. Training: a simple training algorithm for vector quantization is, pick a sample point at random, move the nearest quantization vector centroid towards this sample point, by a small fraction of the distance, repeat. A more sophisticated algorithm reduces the bias in the density matching estimation, and ensures that all points are used, by including an extra sensitivity parameter. Increase each centroid's sensitivity by a small amount, pick a sample point at random, find the quantization vector centroid with the smallest, move the chosen centroid towards the sample point by a small fraction of the distance, set the chosen centroid's sensitivity to 0. Repeat. It is desirable to use a cooling schedule to produce convergence, see simulated annealing. Another method is LBG, which is based on k-means. The algorithm can be iteratively updated with live data, rather than by picking random points from a dataset, but this will introduce some bias if the data are temporally correlated over many samples. A vector is represented either geometrically by an arrow whose length corresponds to its magnitude and points in an appropriate direction, or by 2 or 3 numbers representing the magnitude of its components. Applications: vector quantization is used for lossy data compression, lossy data correction, pattern recognition, density estimation and clustering. Lossy data correction, or prediction, is used to recover data missing from some dimensions. It is done by finding the nearest group with the data dimensions available, then predicting the result based on the values for the missing dimensions, assuming that they will have the same value as the group's centroid. For density estimation, the area volume that is closer to a particular centroid than to any other is inversely proportional to the density. Use in data compression equals, vector quantization, also called block quantization, or pattern matching quantization, is often used in lossy data compression. It works by encoding values from a multidimensional vector space into a finite set of values from a discrete subspace of lower dimension. A lower space vector requires less storage space, so the data is compressed. Due to the density matching property of vector quantization, the compressed data has errors that are inversely proportional to density. The transformation is usually done by projection or by using a code book. In some cases, a code book can be also used to entropy code the discrete value in the same step, by generating a prefix-coded variable length encoded value as its output. The set of discrete amplitude levels is quantized jointly rather than each sample being quantized separately. Consider a k-dimensional vector of amplitude levels. It is compressed by choosing the nearest matching vector from a set of n-dimensional vectors, with n